Hi guys, so this video is going to show you how, in simple terms, a mission to the moon can be achieved. We're going to start off using this nice, sort of cute little physics simulator to take us through all the steps that we need to in order to take a rocket from the Earth to the moon. So here's our Earth in the simulation, planet, or rather a planet much like Earth, and over there is our target, the moon. And this is where we're going to go. Okay, so there it is. That's where we're going to end up. So somehow we've got to get off the planet, out into space, and up to the moon. Okay, now this is, being a simulation game, is not exactly the same as the real Earth and the real moon, but it runs on the same rules, so we can use it to learn about how we're going to take a rocket into space. While you're watching this, I suggest you make a few notes of some key terms, and you keep an eye on the tasks that are elsewhere in the lesson on the webpage you got this video from, and you also may want, of course, to rewind, go back, watch bits of it again to make sure you've got the idea. So, let's get started. Okay, just before we start, I'd like to draw your attention to some of the nomenclature of a rocket. We've got, on the sides of the rocket, 4 solid fuel boosters, big solid rocket engines, a bit like a firework. They can't be turned off, but they're very powerful. In the centre of the rocket we have the core, which is our main fuel tanks, and at the very top we're going to have the payload. Payload is in this case, is our small capsule with our astronaut in it that's going to get us to the moon. So this is the rocket that is going to take us to the moon. Okay, as you can see, it's quite a big piece of kit, consisting of some rocket boosters at the bottom, these 4, a main body, and up at the top inside this section is the actual lander that is going to land on the moon. So if I lift that off, this section here, this top section, is the section that is going to take us to the moon eventually, and is going to come home. Everything else is just about getting into space. As we will see, getting into space is actually the hardest part. Once you've got yourself into orbit, you're pretty much, halfway to anywhere. So, when we launch it, we're going to use all of this bottom section to get us into space and get us towards the moon, and then the craft in the top section, which is going to have our astronaut in it, is going to get us up there. To give you an idea of how big these things are, we can see here in this little vessel mass, 138.13 tons. So that's pretty heavy. Well, that's what, 138 adult elephants. It's pretty big. So let's take it to the moon and see what happens. Okay, so we're now ready to launch the rocket. While we're sat on the launch pad, there are 2 forces acting on the rocket, essentially. There's its weight, due to gravity, and the reaction force pushing up on it from the ground, so it doesn't fall through the launch pad. We know that because we know Newton's third law says that every force has an equal and opposite force. So I'm just going to pause the video now and draw on the equal and opposite pair of forces. So in this case, we have the weight of the rocket, which is the force due to gravity, pulling it down towards the centre of the Earth into the launch pad, and we have the reaction force from the launch pad pushing back against the rocket because of Newton's third law, which is equal in size, opposite in direction. They cancel out, so the result is 0, and our rocket doesn't move, or rather it stays still. We're now ready to launch. So, when we launch, these boosters are going to light, these 4 solid boosters are going to light, they're going to fire us up into the air, and because the thrust from them, the force pointing upwards, is going to be larger than the weight, plus any air resistance acting against us when we move, we're going to start to accelerate upwards. Okay, so let's launch. On. As you can see from this little box here, we are now accelerating upwards, moving upwards at about 16 meters per second squared, accelerating, and our speed is increasing. I'm just going to pause the video again to examine the forces on us at this stage, because now we're moving, we've got thrust and air resistance drag involved. So there are 2 things going on here. The first thing to note is why we have a thrust force. The rocket is throwing out gas out of the bottom, shown here. That gas is hot exhaust gas from the engine. Now, the rocket exerts a force on that gas, downwards. So Newton's third law tells us that there must be an equal and opposite force on the rocket upwards. Okay, so the rocket moves upwards. That's going to be thrust. And I'm going to show it here with an arrow. Now, in order for us to be speeding up, accelerating upwards, there must be an overall force on us upwards, a resultant force upwards. That means the thrust, shown here in blue, has to be bigger than the sum of, the total of the rocket's weight and the drag on it because of air resistance, shown here. So long as this is true, there will be a resultant force upwards, thrust will win, and we will accelerate upwards. If this ever stops being true, of course, we'll start to slow down and eventually might start falling. Okay, so we've looked at these forces. We're now burning fuel. Now, our acceleration, as we said, is equal to the force divided by our mass. The force is coming from the engines, and obviously is made less by air resistance and weight. And our mass is the mass of the vessel, which you can see here, the mass of the rocket, which is about 95 tons. These 4 boosters are going to burn out in a minute. When they do, when they can't burn out anymore, they're going to be dead, useless mass. So we have to get rid of them. Otherwise we wouldn't be able to accelerate properly. So we're going to ditch them, and you'll see them ditch about now. There we go. So we've just reduced our mass significantly. Now we've reduced our mass, we can continue to accelerate upwards again. Newton's second law, acceleration is force over mass, still applies. The rocket itself is turning over now. This is because when we go into orbit, we're going to be going east, essentially. So, I'm just going to pause the video again to examine the forces on the rocket as it rolls over. Very briefly, weight is still pointing directly down towards the centre of the Earth. Thrust is now pointing in the direction the rocket's thrusting, the direction the engine is pushing it, and drag due to air resistance is pulling back against that thrust. This is called a gravity turn, by the way, in rocket science. This is essentially we're using the force of gravity to pull us over to help us get into orbit. You'll see we're still burning fuel here. When this section burns out, there's another rocket engine in here, which will drop as before. So, here's the map. We're aiming to get our apoapsis, which is our highest point of our orbit, up to 90 kilometres, because when that's at 90 kilometres, that means we will get out of the atmosphere and we can be in space. Another thing to note is that air resistance is going to be increasing as we go up, because we're going faster. However, it's also going to be decreasing air resistance because the atmosphere is getting thinner. There's less air up here. Comes to the drop, so there we go. Just drop that useless empty fuel tank again, and now we're on a smaller engine. And we're just going to boost the last stage. You'll see that we are now going about 1500 metres per second, and that the highest point of the orbit is approaching 80 kilometres. Only got a little bit further to go now. In a moment, we're going to turn the engine off, and I'm going to pause the video again to examine the forces on us. So there we go, there's engine shut down. Now the engine is shut down, the only forces acting on us are weight, in red, and drag due to air resistance, in grey. That means the resultant force on us will be back and downwards. So we're slowing down. If we don't do anything, we're going to fall back to Earth eventually. Just like a ball thrown in the air will fall back to Earth. Okay. So, there's the moon, our target, up in front of us. And we're just going to drift now. Slowing down, because of the force of weight pulling us back, but slowing down now. This up here is a use of the rocket engine. We're going to burn the rocket engine to speed us up, to accelerate, again using Newton's second law, acceleration is force over mass. The force from the engine is going to push us to be going fast enough to get into orbit. So here's the engine's burning, and again we've now got no air resistance on us, just got the weight plus the force of the engine. We're out of the atmosphere, you see, and you will see as we speed up, 2,100, come up to 2,200 metres a second, our path goes out past the edge of the planet, and eventually we're going to stay in space. We're now going so fast that we won't actually hit the ground. This is called a free fall path, or an orbit. As you can see, we're going to fall towards the ground under gravity, because that's what we'll do, but we're going to every time we fall, we don't actually ever hit the ground. We just keep going round and round and round, because we're high enough up and fast enough. And let's examine the forces on us again as we do. So there's the ground down there. Okay, and let's just examine the forces on us. Are there any? Or are there some that we don't worry about? Okay, so we're essentially at a constant speed now. There is no force forwards or backwards acting on us. Our weight is still pulling us downwards. But, as we noted before, we're not actually ever going to hit the planet, we're in an orbit. But because we're in, essentially, free fall, we feel like we're weightless. The little guy inside my spacecraft down here would be floating if he wasn't strapped into his seat at this stage. Okay? But he's not feeling no gravity. He's feeling less gravity than on the surface because he's higher up. But he still feels the force of gravity, his weight, although he doesn't notice it because the rocket is falling at the same speed he is. Another thing to note is because there's no air resistance, no other forces on us, if we start, for example, spinning, we won't stop. So if I spin my rocket around like this, it's going to keep rotating until I apply a force to stop it. It's just going to keep doing that forever now because no force stops it. There we go. I've just stopped it. Or if I rotate it this way, if I start it spinning, like that, it's just going to spin around. Now this is because Newton's first law says an object moving at a constant speed will continue to move at that constant speed until a resultant force acts on it. Now, there's no resultant force on my rocket. It's out of the atmosphere, it's in free fall, and there's no air resistance. So it's just going to continue to spin. And you'll notice here it's still at a pretty much constant speed until I apply a resultant force, which I'm going to do now. There we go, the rocket won't do anything. So this is just the rocket's internal control system trying to spin it back into some sensible alignment. Now, as noted, we're at a constant speed now. So we can't go anywhere unless we use our engine. We apply a force, and you can see here the maximum thrust force the engine can produce is 600 kilonewtons. That's 600,000 newtons. And so that force is going to be our force applied on our mass of 21.57 tons to get us moving. So let's examine how we're going to get to the moon now. So here's our target, the moon, which in this simulation is called Moon. So here it is. I'm going to just highlight that in green. So we are currently going at 2,262.4 meters per second. To get to the moon, we need to be going at we need to get to an altitude of 11,400,000 meters. Although you'll notice the moon is actually going slower than we are. It's going at 542.5 meters a second. It's because essentially the further out you go, the slower you'll be travelling. However, we are going to have to accelerate to get ourselves up into a higher orbit, to get us up to the moon. So let's work out how we're going to do that. There we go. And for those of you who are interested in a little bit more about actual rocket science, this orbit we're going to use to get there is called a Hohmann transfer orbit, because it was invented by a guy called Hohmann, who was, I think, Dutch, but he might have been German. And it's a specific kind of orbit that is going to take us to our target. So here is the point we're going to start to use the engine, and we're going to thrust to the right to speed ourselves up. And this is how much we're going to have to change our speed, by 844.9 meters per second. That's how much we're going to have to speed up by. And that's just the radio on the rocket. So let's get ready to do it. I'm going to spin us around until the point where we use the engine, and then we're going to pause the video and examine the forces again. This is going to be the transfer stage of the orbit. We've done the boost or ascent stage to get us into orbit, and we're now going to complete the transfer stage in a moment. This dotted line is the path our rocket is going to take. So here we are, moving towards the point at which we're going to use our engine. And remember, our capsule with our guy in it, our Jebediah, our astronaut, is inside this fairing here. So, I'm just going to pause the video to examine the forces on us now. Okay, So as you can see, as we have that resultant force acting forwards, we're speeding up. Our speed has gone up, we've still got a bit further to go, and our path that we are travelling on is getting further away from the planet. Eventually it's going to match this path here. There we go. Nearly there. And hopefully this will put us in the right place. I may have to. So, we've now sped up. We're now doing 3,102 point something meters per second, and we're en route for the moon. The moon is here currently. It's going to be here when we meet it. So, let's just stabilise. While we're on our way, I'm also going to ditch the fairing so we can see our little rocket in our little vehicle inside there. And then I'm going to cut the video forward to the point where we reach the moon. So, I'm about to apply a large force to blow these fairings off the sides of the rocket. You will notice that when they feel that force, they accelerate rapidly away from the rocket. And of course they don't slow down, because there's nothing up here to slow them down. There's no air. So let's watch them do it. There we go. And they're just going to keep going away at that constant speed until another force acts on them. And in here we can see this is the part of the rocket that's going to land, and our crewman, Jebediah, is in here. So, there's the moon ahead of us. I'm going to cut the video forward now to the point where we reach the moon, because that's the next point at which anything interesting happens. We've previously been rising away from the planet Earth. We are about to, after this point where we encounter the moon, we're about to start falling towards the moon as we get caught by its gravity, and the moon starts to be the dominant force over us. So, when that happens, the view is going to change. And we're going to start falling towards the moon. As you can see, this path here sort of shows our changing path as the moon pulls us in with its force of gravity. Force due to gravity, I should say. So there we go, there's the transition. We are now in what we call the sphere of influence of the moon. It is now affecting us more than anything else. And as you can see, currently we're going to fall towards it along this line. We're going to have a lowest point called a periapsis there at 71 kilometres. And then we're going to rise up again. And if we don't do anything at the moment, we will fly away from the moon again, and we'll end up back on this big orange trajectory, just in a big orbit around the Earth again. So we've got to do something. We're going to have to use our engine and apply Newton's second law again. Acceleration is force over mass. We're going to have to apply force to change our speed. I want you to have a think. Are we going to have to speed up or slow down in order to get into orbit around the moon? Give you a moment to think about that while I put the commands into the spacecraft to get it to do this. Right, so now we're falling towards the planet. I'm just going to speed up time so we fall towards the planet. And hopefully you've come up with an answer to whether or not we're going to need to speed up or slow down. We are currently going very, very fast, so faster than the moon's escape velocity, fast enough that we'll escape if we don't do anything. So we're going to have to slow down, and you'll see we're going to have to slow down by 245.5 meters per second. So, let's go back to our spacecraft. Here it is. We're pointing opposite our direction of travel now. We're travelling to the right of the screen here. And I'm just going to pause the video to show you the forces when the engine turns on. Okay. So we're now slowing down, and you'll see we're now captured in an orbit around the moon. And this blue path is our orbit. You'll see that our orbit looks like our orbit did around the Earth. We're falling towards the planet, but we never actually hit it because of how fast we're going, 500.8 meters a second, which is much less, about a quarter of that we needed to go around the Earth. We have this large spacecraft. Now this can't land, of course, because well, it's got no landing legs. The landing legs are up here, so we're going to detach the fuel tank that we don't need anymore from the rest of the spacecraft. We're going to detach that, and then we're going to land this part. So detached it and separated myself. Now, we need to land. So, here we are in orbit. We are going at 500 meters a second. We are going to need to slow down to land. So, to do that, we're going to need to use the engine again. I'm going to set a place to land, and then we are going to come in and land at that place, and we're going to have a look at the forces during landing, which is going to be sort of the middle of our mission. So I've entered target coordinates, where I would like to land. It's just there, on that red dot. And to do that, we're going to move around to the other side of the moon. We're then going to round about here. We're going to use the engine to slow us down by burning the thruster, the engine, in the opposite direction to where we're going, and just like braking in a car, this is going to slow us right down. Remember, currently, we're not feeling a resultant force. We're in orbit, we're in free fall, and there are no resultant forces on us, so our speed is not changing, or at least not changing meaningfully. So it's hovering at around about 500 meters a second. There will be some small change in speed because our orbit is not perfectly circular, but good enough. Our rocket is now going to use the engine to slow down, so we can pause the video to show you the forces. As you can see, we're slowing right down now, and our path is coming towards the point where we want to land. As you can see, we're now falling. We're in what we call a ballistic trajectory. Like a missile or a cannonball, I suppose. We're just going to fall, and if we don't do anything, we're going to crash. We're going to accelerate towards the moon, and we're going to crash. So here we go. We're going to need to use the engines, and luckily my landing computer is going to do that for me. Why don't you consider what would happen if my engine wasn't strong enough to counteract my weight? So here we go. I'm just going to pause the video to look at the forces again. There we go. Cut forward a couple of minutes, I think, just to the point where we hit the ground. As you can see, we're slowing right down. Now, we're falling currently. The engine's turned off, so we are simply falling. We're going to need to use the engine again before we hit the ground. And we'll do the same again when the engine turns on in the final burn. Okay. And here we are coming in to land at a nice sedate 0.5 meter a second. So there we are, we've landed. Happily and safely on the moon. And again, let's consider the forces on us now. So, let's have a look at what the acceleration due to gravity is here, the strength of the moon's gravity. If I turn this little device on, it'll tell me it is 1.58 meters per second squared. So, about a sixth that of the Earth. And that is one thing that this simulation game gets right, is that the gravity of the moon is about 1.6 meters per second squared. So I'm going to get my little astronaut out, and I want you to have a think about his weight. Will it be more or less than it was on Earth, his weight? Here he is. Now, as we've seen previously, he will be able to jump differently on the moon. He has got a much, hopefully you just said a much lower weight, and therefore he will be able to jump much higher, approximately 6 times higher, roughly. So let's see if he can do that. And yeah, it turns out he can. There's obviously no way in that spacesuit he'd be able to jump anywhere near this high on the Earth. But on the moon, he can jump really quite high indeed, and make long, sort of bounding leaps if he wants to. And there are some great videos of real astronauts from the Apollo missions on the Earth doing this. Okay, that beeping, by the way, is just telemetry, it's radio data. So, Let's plant a flag and go home then. Now we've seen that we have a lower weight. Just plant a little flag. There we go. There we go. And that, by the way, is the name of the simulator I'm using. Kerbal Space Program. So, having planted our flag, let's go home. Now, one of the key things about coming home from the moon is how much fuel we're going to need, and how much thrust from our engine. We've got a much lower weight here, because the strength of gravity is 1.6, about, rather than the 9.81 it is on the Earth. So we're going to need a lot less fuel to get home, which is lucky, because we don't have a lot left. We've only got one fuel tank, and it's about 2/3 full. So, is that going to be enough to get us home? Let's see. Let's find out. So as you can see, we accelerate extremely rapidly because gravity is much weaker here. So we're actually accelerating at 17 meters a second already, even with this tiny little engine. And the highest point of our orbit, is going to be getting up to 60, which is what I want it to be, very rapidly. Two reasons for this, and I'm going to pause the video to show you why. So, there we see it, because there is both smaller gravity, so a smaller weight, and no air resistance on the moon. Which meant that whilst landing was trickier, because we couldn't rely on the air to slow us down, getting back up into orbit is nice and easy. So again, we're just going to drift, and now use the engine to make our orbit a circle. Again, I can pause it to show you that. And we see that quite soon our orbit is going to be a circle. And there we are. There we have it. A circular orbit above the moon. So, time to come home. Now, to come home, we need to think carefully about what direction we need to move in. We're currently travelling, in this case, anti-clockwise around the Earth. We're with the moon, we're travelling anti-clockwise. Okay? And we need to get lower. We need to lower our orbit, which means we need to thrust clockwise. So, we're going to start here when we're travelling clockwise, at that point there, and we're going to use our engine until we get back to the planet. There we go. And I'm going to put that so we drop nice and low, 8 kilometres above the surface, which means the atmosphere will slow us down. And that's going to take me, I have to change my speed to accelerate by 288.6 meters per second. Okay? And that's going to take me home. So here we are. We're about to enter the atmosphere. Okay? And there's my spacecraft communicating with base. So we're about to hit the atmosphere. When we do that, we're going to slow down rapidly. And there's going to be a few other interesting things that go on as well. So, here we are entering the atmosphere. As you can see up here, the atmosphere is starting to get thicker. We're 50 kilometres up. I'm just going to pause the video to examine the forces on us now. Right, so we're starting to feel air resistance, and as the atmosphere thickens, that air resistance is going to get very, very large. So large, in fact, because of our very high speed, that the air starts to get superheated around us. This is because of compression of the air at the tip of the rocket. As you can see, it's glowing red hot. So let's just pause the video to examine those forces again. So, because our air resistance is greater than our weight at this stage, we are slowing down. As you can see, we are slowing down very rapidly indeed, and it's quite a high g-force. High acceleration. There we go, we're accelerating at 21.37 meters per second. That's how squared, that's how much we're slowing down. This will be profoundly uncomfortable for our little astronaut, because he will feel approximately 2 and a bit times heavier, crushed into his seat. And but as we slow down, we know that air resistance gets smaller the slower you go. So we slow down, and that heating effect, that compression heating effect, starts to go away, and we stop glowing. Now, we're not going to land this whole spacecraft, because otherwise that'll probably explode, because we've still got a bit of fuel left. So we're going to have to drop it. The last thing we're going to do is we're just going to drop this section, and then float down on our parachute. There we go. So I've just dropped it, and I'm now going to open my parachute. Fully opened parachute. Let's examine the forces again. There we go. And we're just going to drift down until we splash into the ocean now. I'll cut the video forward until that happens. So, here we are. We're about to hit the ground. There'll be a brief resultant force as we stop, and then we'll go back to no net forces. So here we are. We've hit the ground, the parachute's been cut away, and we're now floating. So the last thing we have to consider is the forces on us as we float. So that's it. That's how we go up into orbit, to the moon, and home from the moon. I hope you've enjoyed watching it, and there are now some activities some quick activities to have a go at on the page that this video is embedded in. Feel free to go back and watch it again, of course, and take any notes if you think you need to. Alright, thanks for watching. See you later.